morning. We are really privileged to have amongst us two very special people. And before beginning the session, I would like to introduce today's chair, Dr. Sundar Mukherjee, our very own. And I'd be giving you a brief introduction and hand it over to him to introduce our main plenary lecturer today. So, Dr. Sundar Mukherjee is an assistant professor at the Statistics and Mathematics Unit at Indian Statistical Institute, Kolkata. And prior to this, Dr. Mukherjee joined ISI as an Inspire faculty at the Interdisciplinary Statistical Research Unit and also spent a couple of months as a visiting senior research fellow at the Department of Mathematics, National University of Singapore. He finished his PhD in 2018 from the Department of Statistics at UC Berkeley, and his research interests include probability theory, including random matrices and spectral analysis, random graphs, network models, statistics in general, and statistical machine learning. So, Dr. Mukherjee, I'll hand it over to you to introduce our plenary speaker.
Thank you, Anish. Am I audible? Hello?
Yes, you are audible. Yes.
Okay, great. So it's a pleasure to have Professor Rémi Flamary from the École Polytechnique as the plenary speaker here. Professor Flamary is a full professor in the Department of Applied Mathematics at École Polytechnique. His research sits at the intersection of signal processing, machine learning, and optimal transport, and their application to various areas such as biomedical signals, brain-computer interfaces, and so on. And he is probably the most well known for being the co-creator of the Python optimal transport library, the POT library. So today he is going to talk about optimal transport for graph representation. Professor Flamary, the floor is yours.
Hello, thank you for the introduction and thank you for the invitation. So I'm going to start. Yesterday we'll talk about optimal transport and graphs together. Especially we're going to talk about unsupervised learning, so basically representation learning of whole graphs, so not node embedding, but graph embedding, and also about graph prediction and how recent approaches using neural optimal transport solvers allowed to scale to large data sets and or large graphs. Okay, so nowadays graphs are everywhere. So a bit sorry for these slides that everyone puts everywhere, but that's still true. Okay, so the data we have often has a structure, and this structure can be seen as a graph. So social network have connections, drugs, materials, molecules have obviously a structure with connected atoms. 3D meshes are also graphs, brain connectivities, transportation network. A lot of real life data and real life systems actually rely on graphs. And so, of course, we work on that for a long time in signal processing and machine learning to model properly the interaction between the structure of the graph and the signals on the graph, that is, the values on the nodes of the graph. And so the traditional way to do that is usually to look at the Laplacian of the graph. That is, we look at a spectral representation of those graphs. So when you look at the Laplacian of the graph, you look at the representation of the structure, the connectivity between the nodes, and on top of that, you have a signal that is the value on each of the nodes on the graph. Okay, and so the way things are done usually, so in graph neural networks, for instance, is to do one step where you use a structure, use the Laplacian, basically you spread information on the graph using the connectivity, some kind of discrete diffusion process on the graph, okay? And then you use the network that do nonlinear transformations. And so if you think about it a little bit, you see that basically we split the structure versus the local, non-linear representation on the nodes. And when you do that, well, that's how GNN works, and that's a very powerful way to do that. But basically, because you do two different steps, one that takes into account the structure and one that takes into account the signal, some kind of independently, so in a sequence, okay, because it's a multi-layer neural network, but still, you don't look at the whole graph at any point. Okay, and so that was one of the most important questions we wanted to look at when we started to look at optimal transport on graph, is to model the whole graph as one object, that is a distribution. And so that's going to be the main idea of the whole presentation. I'm going to give you some introduction of optimal transport between graphs, especially about what's called the Gromov-Wasserstein and the fused Gromov-Wasserstein distances, how you can relax some of the constraints, and I'm going to tell you how you can do that to do basically graph alignment. So it's a special case, or maybe a more general case of graph matching. And then we're going to talk about how you can do machine learning with those new tools, how you can learn representation, and you can do what is called structured graph prediction. That is a neural network that actually predicts a graph from anything, from a spectrum or something else. And in the last part, we will see how you can scale those optimal transport solvers to modern applications with large number of graphs or larger graphs. Okay, so first, I told you we want to represent a whole graph as a distribution. And so the main idea is to say, okay, so let's see each node as a Dirac. Okay, so it's a probability distribution. It's going to sum to 1. You're going to put weights on the Dirac, and each node can be seen as a Dirac. Okay, and so now the question is, how do you encode all the graph information in the feature representation in the Dirac? Okay, so here we separate two things, and that's very important. We separate the structure that you can see here. We suppose that the structure of the graph, so the connectivity between the nodes, is stored in a feature space called Xi, which is usually, we never actually have this feature space, okay? But bear with me for a sec. And we suppose that on the nodes of the graph, you do have features, so can be colors, can be vectors, can be types of atoms, for instance, if we are talking about a molecule. And so we encode the whole graph, structures and features, as a joint distribution, XF, okay, and a weighted sum of Dirac. So keep in mind that here we do optimal transport, we work on distribution, and we need to have sums, we need to have weights on those Diracs so that it sums to 1. Okay. Great. So that's how you represent the whole graph. So of course, if you don't have any structural feature, so if it's not a graph, you recover a classical empirical distribution. Okay, sum of Fi, where Fi are vector embeddings of the nodes. Or if you don't have no features on the nodes, okay, you can just encode the structural information. Great. So now, how do you store that in memory? The trick is we never actually have the Xi's, okay, because those are embeddings that depend on the structure, but we can store a pairwise matrix that contains the pairwise relationship between the nodes, okay? So simple examples are, you can store a pairwise matrix D that is an adjacency matrix. It's going to be 1 if two nodes are connected, 0 if they are not. Can be something more complex that also encode more information, such as the shortest path matrix. So in this case, you compute the shortest path along the graph between two nodes, and that's the value in your matrix D. Okay, so if you want to store a graph in memory, you're going to have a pairwise matrix that encode the relationship between the nodes in the structure, F that encode the features on the nodes, F matrix, and A that is a weight vector that encodes the importance of each of the nodes. Okay, so now that I've done that, we can do optimal transport because now we do have a distribution. And we're going to start with graphs that have no features. And so there is something called the Gromov-Wasserstein distance that's been proposed by Memoli in 2011 that extended traditional optimal transport. So I won't have time to introduce classical OT, but this is the Gromov-Wasserstein problem. The idea of the optimal transport problem is to find an optimal transport plan, that is a matrix of size, number of nodes on the left, number of nodes on the right. You can see here an example of this matrix, okay? And you want to find this matrix that minimize a cost of displacement between two distributions. Okay, and so in the Gromov-Wasserstein case, actually you don't have a cost that tells you how much it costs to move from one node on the left to one node on the right. You only have pairwise relationship on the right and on the left. Okay, so you want to move the red distribution onto the blue one, but you want to preserve the pairwise relationships between the points. Okay, so basically, you're gonna try to find an optimal transport plan. So an optimal transport plan, if you sum the column, you recover the weights on the left. If you sum the line, you recover the weights on the target. Okay, so that's the constraints. That's the pi here, you can see here, okay? And you want to find an optimal transport plan, so that moves everyone, that minimize the discrepancy between the pairwise relationship. That is, if 2 points are close on the left, they should be moved to 2 points that are close on the right. If 1 point is far away, it should be moved to 1 point that is far away. I'm gonna show you a quick example of this. Basically, I want to move from this point to those points. I have 2 points. That's one example of an optimal transport plan. Small comment, Gromov-Wasserstein is invariant to rotations because you only look at the distances between the points. So you can see that the black lines that are the optimal transport plan don't change. But you can add more points, okay? So here I put 3 of them. Here I can add 3 again, and you can see that again, it's gonna recover something interesting. That is, these points that is far from everyone will always be moved to this point that is far from everyone. Those 3 points that are quite close together will be moved to those 3 points that are close together. Okay, and because you optimize the distance between the pairwise relationship. Okay, great. So that's the problem of Gromov-Wasserstein, and it's a very nice problem. Well, it's nice because it has nice mathematical properties. Okay, so it's a proper distance between distributions. It's actually called metric measure spaces, the technical terms. And so you can solve this problem. So this is a finite optimization problem. Small comment, the constraints are convex, but the problem itself is non-convex. Okay, so whenever you do Gromov-Wasserstein, you're always going to get a local minimum. Okay, so that's a problem for some mathematician. In practice, it kind of works. Okay, similarly that neural networks are non-convex, and yet we manage to find good solutions. But still, be careful. It's always going to be a local solution. You're never sure that it's the best possible solution. And so it's sometimes a bit hard to solve because it's an extension of optimal transport. When optimal transport, you just have a double sum. Here, you have a quadruple sum. Okay, so this is more easy, of course, to solve and non-convex. There are approaches to speed that up, such as entropic Gromov that will add an entropic term that will speed up potentially the solution at the cost of making the OT plan non-sparse, which, I mean, sparse OT plan are nice because you know that 1 point goes to 1 point or a few points is something that is interpretable. If you lose sparsity, it's sometimes a little bit less interesting. But here, it works. I can compute similarity between 2 graphs, but 2 unlabeled graphs. Okay, they don't have any information on the nodes. It's just I want to preserve the structure of the graph, not the features. So that's why with Citron-Envoyé, we proposed an extension of this where you want to preserve the pairwise relationships, but you also add a linear term. So this is a classical Wasserstein term where you can compute similarities between nodes in the feature space. And so now you have a parameter alpha that put more or less weights on the pairwise relationship or the Wasserstein term, okay? And it allows you to basically weight how important are the features on the nodes or the structure of the graph. And so if this is 0, if this fused Gromov-Wasserstein is 0, it means that you can find a one-to-one mapping between the points that perfectly preserve features on the nodes and pairwise relationship. Okay, great. So now, small comment. You can do optimal transport between graphs, as I told you. You can do optimal transport that's going to measure how close two graphs are. It works between graphs of different sizes. So this is very interesting because basically as soon as you have a mass of 1 on the left and on the right, you don't really care how many nodes you have on both sides. So it works across different sizes and it has nice geometrical properties. So the kind of thing you can do with that, those were the first applications, and I'm gonna describe a little bit those. For instance, you can look at the surface, compute shortest path on the surface, so some kind of a geodesic on the surface, okay? And find alignment between those two surfaces, and you see that the orange part, top of the head, goes to the top of the head. If you have very different structure, it still goes to the top of the head as long as it's humanoid. And you can even go from 3D surfaces to 2D distributions, and it's still gonna preserve the geometry, because that's what Gromov-Wasserstein does. It wants to preserve the pairwise relationship between the point, the geometry. So that was, in my opinion, one of the first very impressive results that you can do with that. Something that was also very impressive was that it can be used also to align between different embeddings in different spaces. Okay, so if you learn a word embedding in English, a word embedding in Italian, okay, so of course some words are close together. So in this word embedding, you can compute a pairwise distance matrix, and you do the Gromov between those two distributions of words. You're going to find alignment that actually preserve the semantics. So, for instance, as you can see, the word tu was moved to the word due, which was the two in Italian. Okay, so basically, in a totally non-supervised way, you could find correspondences across different languages in word embedding. Okay, so the thing with OT is that, as you should remember, there is this constraint matrix. All the mass needs to be moved from left to right. And that's both very interesting and it can be a limiting factor, because sometimes you have different amount of weight. For instance, if I come back to my example, here, sorry, I add a few points, okay? Clearly, here I have a cluster, here I have a unique point, here I have a cluster, here I have a unique point. Intuitively, I wouldn't want this point to be mapped to here. I would want that to be mapped only to here, okay? And why is that? Because of mass constraint. Basically, this point has too much mass to go fully here, okay? And so those mass constraints will lead to some limited things, and that in some application, when you have different masses or different surfaces on the surface on the different structure, you want to relax those constraints. So you've got variants of that called unbalanced Gromov optimal transport, which consists in basically, instead of having hard constraints, you penalize the violation of the constraints, and you weight this penalization. So those are called unbalanced Gromov-Wasserstein, or you can be even more aggressive and just remove one of the constraints on one side. I'm going to show you what it does. Oh, sorry. Okay. I'm going to back here. Okay, so now let's say you have those here. Okay, if you do Gromov, you're going to have something nice. Basically, you have two clusters, 2 points. The point from one cluster goes here. Okay, and you remember with the traditional Gromov, if you add 1 point, you're going to have problems because of the mass. And this one is the semi-relaxed Gromov. And look at what happens. If you have more points, it's just going to reweight this node so that it can get more mass. Okay, so it's a way to better preserve the relationship between the nodes. Okay, and if I add 1 here, it's going to get a 0 mass because you only have 2 clusters, and it does not make sense to put some mass here. Okay. Great, so those are variants, and they have been used in a lot of applications, and one that I think is very interesting is application on brain data. So the recording is done like this. You record with functional MRI, okay? Activities of the brain of someone doing a mental task. So it can be counting, can be trying to memorize something, can be math, depends, okay? So different mental tasks. And so you can measure the activations of the brain. And you can, of course, it's an MRI, you have a surface of the brain. And the thing is, between two humans, we have different surfaces. They look the same, but those are different surfaces. And so the question is, how do you find correspondences? Okay, which area in the brain of one person correspond to which area in the brain of another person? And that's a difficult question. So what people have done up to now, up to a few years ago at least, was to take this brain, blow it like a balloon. Okay, you make it a sphere. You take this brain, you blow it like a balloon, and then, I mean, you have correspondences between both those spheres. Okay, so it kind of works. Okay, but actually, when you do that, you forget about the structure. Okay, because you just go from a nice, curve surface to something that has no curvature. Okay, or much less. Okay, so the idea is to do optimal transport to find correspondences between those two branes that both preserve the pairwise relationship between the points, the geometry, and the features, the activation on the brain. And so we applied that. It was quite nice because we basically estimate a plan on one mental task. Okay, so it gives you correspondences, and then you can use this plan to actually predict activation for the second person on a new task that is done by the first person. Okay, and so we measure the correlation of our prediction, and by doing optimal transport, you can get up to 10%, 10% more in terms of correlation than the baseline I talked to you about. So that's one application. And also why the unbalanced part is important here is that every person has obviously a different surface in their area. Okay, if one of your area is activated during mental task, it's not going to be exactly the same surface as they have the mental task of another person. So that's where exact OT would be a problem, but unbalanced would be a good idea. Okay, so I'm done for the first part, introduction of OT and a few ideas of what you can do with it. Now I'm going to talk to you about what kind of machine learning you can do using OT on graphs. So one very simple thing you can do is now you have a distance, okay, between those graphs. You can actually compute a barycenter, a mean of those graphs. Okay, so it's a Fréchet mean. It's an extension of the Euclidean barycenter, but with the Gromov-Wasserstein distance. So the idea is you have several graphs represented as the pairwise matrix and a weight, and you want to find the pairwise matrix and the weight that is closer to the weighted sum of those graphs. Okay, so an example here you have 8 graphs. So those graphs are basically, as you can see, circles, but with a little bit of noise, both in terms of connectivity and on the signal. And if I compute a barycenter, this is what I get. So basically, you recover something that clean up the specificities, that is, in this case, the noise of those graphs, but still keep the main information on the graph. And small comment here, D and A can be any size. So you can ask for it to be a lot of nodes or to be smaller number of nodes, that is, doing graph compression. Because the OT distance can be applied between graphs of different sizes. Another example for a more complex graph, here is not a circle, it's those eights. If you compute the barycenter, you're going to recover this kind of thing. And also, small comment, if you can compute a barycenter, it means that you can compute a mean. So it means that if you have a data set of graphs, you can compute a k-means. Okay, but instead of having a Euclidean mean, you use the fused Gromov-Wasserstein mean. And so, small example here, if your dataset contains fully connected graphs and graphs with 2 clusters, if you run a k-mean, you're going to recover after a few iterations those 2 means, that is very close indeed to the 2 clusters in the original dataset. Okay, so now you have this nice tool that is a barycenter that allows you to basically explore a space. Okay, when you have a barycenter, you have a parameter that is lambda here, that is the weight of those points. And of course, the more weight you put on one of those distributions, the more the barycenter will be close to this distribution. So by using a barycenter, you can basically interpolate, in a multivariate setting between all those corners. And so you can use that as a model to represent your data, to do some kind of PCA, if you wish, okay, or what's called also a dictionary learning. So what I'm trying to tell you is that you use the barycenter constructing the graph is solving the barycenter. So you can basically represent a graph as a lambda, as the vector lambda that encode your position on the simplex in the barycenter. Okay, so you can use that to learn representation of graph, continuous representation of graph that are discrete objects. And so you can use this representation to do graph classification or tons of other things. Also, another thing you could do is use this distance that is very powerful and that works on graphs of different sizes to perform what is called pooling. In GNNs, if you want to learn a classifier, for instance, that takes a graph and predicts a class, at one point, you cannot stay in the traditional GCN, you cannot keep all the nodes, okay? You have to do a pooling that goes from the whole graph with all the nodes to a vector and so that you can predict a class. And so traditional pooling are very simple, like you take an average, you take a max over all the nodes. So when you do the pooling, you discard the structure. While you can do other types of pooling that are a bit more involved, that consists in computing the distance to templates, okay? And you can learn those templates. So it's a pooling layer with where the template graphs are parameters that you can learn with gradient descent. And so this method here works very well. I think it's still state of the art on some of the classical graph classification dataset. Okay, now there is another task that is very challenging and that I like very much is the supervised graph prediction task. So it's not a new task, okay? It's been investigated for many years. Basically, the challenge is you want to learn a predictor, machine learning, okay, a function f, that predicts a graph, so that predicts a discrete object, okay, from an input x. So what could be the kind of application? So a lot of things, okay? Knowledge graph extraction, okay? So if you have unstructured data and you want to extract from this data a knowledge graph, that could be a thing. In natural language processing, usually you want also a tree or a graph that represent your sentence. Molecular identification in chemistry, for instance, you can measure a mass spectrum for a molecule, okay? So that's a 1D vector, and you want to recover which molecule actually correspond to this mass spectrum, okay? So it's a classical thing in CSI, you know, when they find something and they want to know what is the chemical component. And so this is a very difficult problem, and the output is a molecule, so it's a graph. And so what people do is usually they use surrogate model. That is, they never actually predict a graph because it's too hard, okay? They embed the graphs, they embed the input, and they learn to predict between the embeddings, okay? So it kind of works, okay? Those methods were actually state-of-the-art for many years. But I think that nowadays, you know, with modern neural network that can actually process those graph objects, we could do better, and that's the kind of thing we try to do. And to do better, the thing is you want to train a neural net, you need a way to measure how good your neural net is. And so now, because we have Gromov-Wasserstein and fused Gromov-Wasserstein, we can measure the error of a neural net, okay? And so that's something we proposed as a first solution. As I told you, you can basically learn a dictionary, okay, of graphs. And one thing you can do to actually reconstruct a graph from that is to do a barycenter. So the idea was to say, let's learn a dictionary, D-bar, okay, so those are graphs, okay, so that my prediction function is actually the solution of a barycenter. And I've got to learn a neural network that will predict the weights in the barycenter, okay? And I'm going to use the Gromov-Wasserstein as an error term to do that, okay? And so that was very nice. We could learn a quite complex function, okay? So that this is a neural network that actually predict graphs, okay? We were quite happy with that, but it was very slow because of this barycenter. Because of course, if you want to solve a Gromov-Wasserstein barycenter, it's going to take some time because you need to solve quite complex optimization problem. So we took a step back and tried to design something more efficient than a barycenter to predict a graph. And the idea is the following. You want to predict this graph, okay? So the thing is, this graph can be any size, okay? You don't want to predict only graph of size 10 nodes, okay? So it can be any size. So in order to predict properly, usually what you do, so this is a graph, this is the adjacency matrix, you do padding, okay? That is, you say, okay, I'm going to predict a graph up to a given size. So here you do padding, and now you don't have just one matrix that encode the adjacency. You have also a padding vector that tells you which nodes are active. And you actually don't care about what's here because the node is not active. So that's basically the thing you want to predict. And now you're happy because thanks to the padding, it's fixed size. And so now you can learn a neural net that's going to take an input, and that's going to predict continuous version of those. Okay, so basically continuous version of the adjacency matrix and continuous version of the padding. And now you need to measure similarity between this prediction and the actual data. So now what's important is to put something here that measure similarity between those two, and that is actually a true metric. That is, it's going to be 0 only if the prediction is perfect. Okay. of course, at test time, you're basically going to threshold stuff, and you can threshold both the padding vector and the adjacency matrix, and you're going to recover something. Okay, so this is actually not that much of a new idea. It's been proposed by a paper that's called Relation Former by Schitt and co-authors in 2022. And so they had this idea, but where the idea was limited is that their loss was a bit weird, is that they actually use traditional OT, classical OT, and the linear assignment, Hungarian, to find correspondences between the nodes, and then they plug these correspondences into a loss that looks like Gromov, but then the optimal transport is not optimal, okay, because it's another optimal transport plan that they plugged into the quadratic loss, okay? So what we propose, what you actually use a true fused Gromov loss, actually an extension of it, I'm gonna tell you in a few minutes which one, and to have basically a similar structure, that is, you have an encoder that encodes as a set of features, okay? So those are tokens, okay? You have an input, you encode it as tokens. Then you use a transformer encoder-decoder to actually have now node embeddings. So those are still tokens, but this is fixed size M, okay? That is the max number of nodes. And from those node embeddings, you predict a pairwise matrix, that is adjacency, the feature matrix, and also the masking. And now you see that you have three vectors, A, F, and H, okay? And you might want to say, okay, good, H is the weight, okay? My marginal constraints is the weight on the node, and I'm happy. This is actually not a good idea, because if you put that, you're gonna have some problems. I won't enter into detail, but the idea is those H here cannot be used as weights. What you must do is use uniform weights, and so this is too fast, okay? You use uniform weights, but you need to add this H in the optimal transport cost. And that's what I'm going to do now. Basically, this is what we propose. So it's a fused Gromov, but extended. And the idea is the following. If you have two graphs, okay, one on the left, where you actually predict, so the hat here in red are the prediction of your neural net. The blue is the true data. Okay, so the H is actually a masking. It's binary, okay, in the true graph. Okay, it's not binary in the prediction, but it's binary in the true graph. The thing is, you obviously want to predict the proper masking. Okay, so this is a linear term. You also want to predict the proper features, but only on the nodes that are actually active on the right. You don't really care about the node on the right that have an H of 0. Okay, so you mask also the linear cost with the node on the right for the features. And then you come to the Gromov term that you will also mask with respect to the mask on the right. Okay, so it's basically an extension of fused Gromov where you can mask stuff that is non-important. Similarly, that, when you do, for instance, matrix completion or dictionary learning, you can mask values if you have no data. Okay, and so this is basically what we are doing here, but in an optimal transport cost. And so this can be solved like a Gromov, and so we used it as a loss to fit our neural net. And so this is an example of the loss where you have two graphs. So the true one is this, you have F1, F2, and so a connected graph. And the prediction is going to be 1H, 1 minus H, and here you have F2 twice, okay? And so for the adjacency matrix, we have A and 1 minus A. And actually, it's interesting because if H equal 1 and A equal 1, it's perfect. And if H equals 0 and A equals 0, it's also perfect because you have two ways basically to predict the graph here. And so we're going to move H and A and show that when both are 0 and when both are 1, you see that our cost is exactly 0. But also that is close to 1 when you basically predict badly. But everything here is smooth. So that's something you can optimize. On the right, you see the edit distance, which would be the perfect way to measure actual precision. But the thing with edit distance, it has no gradient. So you cannot use it to actually optimize your loss. Whereas this is a smooth version of the cost. Then the architecture, I already told you, basically a transformers that goes from tokens with any number of tokens to a fixed number of tokens that represent the nodes, and then a graph decoder. Okay, so this is very simple, very similar to actually the paper of 2022. We just force to have a symmetric adjacency matrix because on many of the graph, on our data, at least on our experiments, the graph was symmetric. So it was nice to have that as by design in the architecture. And so we apply that for graph prediction. And so the data were like this. So for coloring, you have an image as input, and you want to predict a graph of connectivity between the clusters, between the segments, color segments in the image. Okay, so two nodes are connected if the segments touch and this kind of thing. US cities is more something like a map. It's a discretized version of satellite data, and you want to reconstruct the map. Okay, so a map of the roads. And so this one is on molecules, GB13, where we go from an embedding of the molecules, well-known way to represent the molecules, and try to predict again, to reconstruct again the molecule. And so with our method, we have very, very good performance, much better than existing methods. Okay, those are edit distances. When they are smaller than 1, it means that with a high majority of prediction, we actually predict exactly the right graph. And we were very happy with those kind of performances. Okay, so now any2 graph is nice, but if you want to train any2 graph, every time you have a batch, every time you have a new graph, you need to compute an optimal transport problem. Okay, and this is costly. Okay, and so the thing is, any2 graph works very well, but it's a bit slow, obviously, on very large data sets. And actually, we couldn't use it on extremely large data sets of graph. So now you have a challenge. That is, optimal transport solvers scale usually cubically with a number of nodes. Okay, even worse usually because cubically is the cost of one iteration in the solvers. Okay, so that's of course something that's gonna greatly limit the size of the graph you can apply it on, and the number of graph on which you can apply it, because every time it's going to be very slow. Okay, so you have basically two directions that tells you if I have a very large graph, well, it's going to be extremely slow, and if I have tons of small graphs, it's also going to be slow. So it really limits the application. But in recent years, people in ML have said, well, optimal transport is basically an optimization problem. And so what we could do is a change of variable. And instead of optimizing, an optimal transport plan, a matrix, with respect to two graphs, this is basically what we do. Maybe we could optimize a neural network instead that encode the optimal transport plan. Okay, and so that's called neural optimal transport. The idea is to say, instead of optimizing over a finite, matrix that is very large, I'm gonna optimize over a neural network that has a lot of parameters, but that I can apply and recover an optimal transport plan. Okay, so that's one first change that you can do. The problem is that this, you still need to solve, for every pairs of graph, because even if you you optimize a neural net instead of a matrix, you still need to optimize this neural net. And so one idea of Amos in 2022 was to do what's called meta-OT. The idea of meta-OT is to say, okay, maybe I'm not gonna learn one neural net every time I have to compute OT. I'm gonna learn one neural net that takes as input the distributions and that will basically predict the best possible solution. Okay, so now you have a neural net that predicts the optimal transport problem. Okay, and so now the theta is for the whole data set, all the pairs in which you want to actually compute the transport. And the beauty of that is that basically you just need to give as input the graphs. It's going to predict for you the neural net. And the complexity of predicting the neural net is obviously only going to be the complexity of doing a forward pass in your neural network that is going to be much more efficient than actually solving optimal transport. Okay, so now I'm going to present two applications of this philosophy. One where we want to solve tons of very small graphs very efficiently, and one where we want to solve on very large graph, and basically both are variants of this. The first one is called Grail. So it was presented at NeurIPS in December. It's called Grail for Graph Level Autoencoder. Okay, and the idea is to take a graph as input, embed the graph as a vector, and be able to reconstruct the graph after from the vector. It's basically an autoencoder, but for graphs. And it needs to work for graphs of different sizes. Okay, and we want here a vector that basically encodes the size of the graph so that you can reconstruct the proper graph. So if you want to do that, you could use any two graph, okay, for this G, and you could use any graph neural network for F. The thing is going to be very slow because every time you need to solve an optimal transport. So here, what we propose is, as I told you, to learn a model that predicts the optimal transport between the two graphs directly. Okay, and so the idea is now, instead of minimizing for every pair, we minimize a model M that works for the whole data set. Okay, and so now we have three neural nets: F, the encoder; G, the decoder; and M that actually find the correspondences between the nodes that you can plug in the optimal transport loss. So no need to solve the optimal transport; you can just plug the plan. And so this works very well, and we apply that on very large data set. And so for, if you see, we compare to other types of graph level autoencoders, and you can see that we have a GI accuracy of 99, so on coloring, which is the data set I showed you, and PubChem 16 and 30 are all molecules in PubChem up to size 32. It's actually 80 million graphs. Okay, so on this data set, which is very large, we could train an autoencoder of graphs that can reconstruct very well. As you can see, the edit distance is 0.78, and so 66% of the time we actually reconstruct perfectly the graph that has been encoded as just a vector. And so now the nice thing is that you have an encoder and a decoder. So you can do interpolation of graph. You basically encode a graph in the vector space, encode another graph in the vector space, and you can interpolate in an Euclidean way in the feature space, and then reconstruct. And you can see, for instance, between this graph and this graph, you can see the trajectory that makes a lot of sense. And basically, actually edit this graph, it's going to remove some nodes, add some nodes, and update the connectivity so that you go from this to this. You can also compute the barycenter, because you can basically encode all the graphs in your data set, compute the average in the embedding space, and then decode. But other types of things you can do that are very interesting, or you can do semantic editing. If in the embedding, you learn a predictor, for instance, that can predict the number of nodes. And then you do steps in the embedding along the gradient of this predictor. It means it's going to displace your vector in a direction that's going to increase the number of nodes. And so you can basically take one graph and say, add one node, add another one, and add another one. And so all the intermediate representation here actually do respect the constraints in the dataset. Okay, so that was the first application. As I told you, we wanted to solve a lot of small problems, okay, up to 32, but on very large dataset with 80 million graphs. Another application we did is called ULOT. Is we wanted now to solve unbalanced OT. So you remember unbalanced, you have the Gromov term, the Wasserstein term, and the penalization. And we wanted to solve unbalanced OT efficiently with neural nets on large graphs. I mean, large, at least up to a few thousand nodes. And so the idea now is still to learn a neural net that predicts the OT plan, okay, similarly to what we did before, but even better to have a neural net that predicts the OT plan conditioned by the parameters. For instance, in Gromov, you have alpha that tells you whether you focus on the structure or the features. You also have rho that tells you how much you penalize the violation of the marginals. And of course, if you change alpha, it's going to change the optimal transport plan. Okay, so now we have a neural net. We propose a neural net that takes alpha and rho as input. The idea being that now you can predict the OT plans for all the values of alpha and rho, and you can validate for free, basically, because it's a neural net that's going to predict the OT plans for you. Okay. Also, the neural net is going to be continuous with respect to all the inputs. It's a neural net, okay, and alpha and rho. So you can do nice things such as you can optimize alpha and rho in a bi-level way. Okay, you can find the alpha and rhos that optimize the second criterion, given that the OT plan is the solution conditioned by alpha and rhos. And so we had a very nice performance. That is, here you can see the prediction of the loss for the numerical solver and ULOT. And you can see that it's very close to the red line, that is equality. So we have very similar performance. So ULOT is a little bit less good. Sometimes when you're above the line, it means that you're not exactly as good as a numerical solver, but it's much, much faster. That is, you can see here, this is time, this is ULOT. And so for the errors that ULOT gives you, the best existing solution would be entropy COTI, and there is like 2 orders of magnitude between entropy COTI and ULOT. So it's much, much faster on application. And so we could apply that on fMRI to find correspondences between brains with different architectures. Okay. Great. So now I'm going to do a quick conclusion. So what I tried to do is to talk to you about how you can represent graphs as distributions. And when you do that, there are natural metrics to measure similarities between those distributions. That is the Gromov-Wasserstein, the fused Gromov if you have labeled graph, or variance if you have graphs that are unbalanced, for instance, with clusters with different amount of mass or amount of nodes. And so know that OT is a very general framework, and that's why there are many, many variants, because you can adapt to the specificities of your data using unbalanced, using fused, these kind of things. But also, I mean, I'm as I said a few minutes ago, I am one of the creators of POT, the Python Optimal Transport Toolbox, and I know how long can be an optimal transport resolution. Okay, it takes a lot of times, especially on large problem. Okay, it's not something that's going to scale very well, and so sometimes you need ways to speed up. So you have entropy that can help you, but it's not going to do everything. And the modern way to do that, I would say, is to actually use neural networks to try to speed up resolution of optimal transport, as you can see, by having like smart architectures that actually predict optimal transport plans for you. You can do nice things, and you have fast solvers that you can apply on new graph, and it's going to scale usually. So ULOT so ULOT, the complexity of ULOT is just the size is quadratic in the number of nodes. And I mean, everything is quadratic in the number of nodes, or else you cannot even look at the adjacency matrix. Okay, so you can have very efficient neural nets that give you very reasonable solutions of optimal transport. Okay, so I also want to thank all my collaborators, so all those wonderful people I had the chance to work with on some of the papers I presented just now. And so, yeah, if you want to use optimal transport, you can check out POT, Python Optimal Transport. It's a free open source toolbox. Kind of works well. Some solvers even run on GPUs if you need those. Okay, so I guess I'm done. Thank you.
Yeah, thank you, Professor Flamary, for the very interesting talk. Any questions? Please unmute yourself if you. Yeah.
Hello, Professor. I would like to ask that can you please shed some light on how you are upscaling from a vector to a graph, and how you are going back from a vector to a graph again? So how do you upscale that?
What do you mean? Go from vector to graphs here, for instance, or?
Yeah.
So basically, the idea of graph level autoencoder is that you have a function f that goes from graph to vector, and a function g, a decoder, that goes from vector to graph again. And we learn all of those together, so that we know that we have a representation here that we can reconstruct any graph from a vector in this space. It's basically it's an autoencoder, okay?
Okay, so G is basically another neural net which is upscaling from the vector to the graph, like.
Yeah, it's not upscaling, okay? It's a fixed size vector and a graph as output. I don't call that upscaling. It's a decoder.
Okay.
Because the vector is fixed size, okay? The size of the vector here is not the number of nodes. Traditional graph autoencoder do that, which I find is interesting in some cases, but you basically learn node encoding, node embeddings that allow you to reconstruct the graph. Here, you don't learn node embedding, you learn one vector that represents the whole graph. That's why it's called graph level.
Okay, so it is a unique representation for the graph.
Sorry, was that the question? I'm
sorry. So it is the unique representation for the graph, right?
Yeah, that's it. Unique that we don't know. Okay, I mean it's a representation for the graph. So we might have problems of decoding. Okay, the decoding is never perfect. It's an encoder.
Okay, thank you very much. Thank you very much, sir.
So, hello, Professor. So, I have a question. So, you are using a padding, right there. So,
Yes.
why you are using padding in that in case of forming the adjacency matrix? And you are saying that the choice for that padding is 110. That will be not a good choice.
No. Okay, so the pairing. So the pairing is basically the optimal transport plan here. Okay, because each node has some mass, and you want to find the optimal transport plan, which tell you, oh, then this node on the left goes to this node on the right. Okay.
Okay.
What I'm saying is, you need to add this here. This basically you want the masking you want to promote the masking to be close to 0 or 1. Okay, that's what I'm saying. Because the problem you have is if you use the masking as weight, because at the beginning of the talk I told you, you can put graph, and then you have those weights AI. Okay, what I told you is basically you cannot use the masking here for a very simple reason is that you're not going to have the same mass. Okay, because the neural net will predict a mass, and the mask on the right will have a different mass. Okay, so basically, if you use that as a mass in your neural net, you're gonna have weird thing happening. Okay, so you need to put the masking here in as a feature basically. But the masking, look, the masking you use it for all the pairs, whereas on the feature you mask the cost of the feature. It's a bit subtle. I don't have time to enter into detail, but we explain that in the paper. We actually give counter example where you can have a zero loss basically and predict something that's not okay. That's what I'm saying. Which in this case is not possible. If you have a zero loss here, it means that you predict a perfect graph.
Okay. I got that. Okay. Thanks.
Okay, Professor, I'm very apologizing that I'm just ask you one more time about this. That from vector to graph. How does the architecture actually looks like? I mean, how do you even go from this vector to full scale graph? Can you please shed some light on the architecture actually?
Yeah, so the ULOT, I'm going to give you the ULOT, for instance. The ULOT is very simple. It's basically we want to predict a pairwise matrix. Okay, so if you have 4 nodes on the right and 3 on the left, we want a matrix that is 3 times 4. Okay, so we design a neural net that can predict something this size. So the way we do that is we have two different ways to do that. We use a GCN to learn node embeddings. Okay, multiple times. Okay, so this is one layer, but this is repeated several times. Okay, so we learn GCN that encode the structure of the graph. Okay, in the node embeddings, and in parallel of the GCN, we do cross attentions. Because basically, if you think about it, a cross attention, when you look at here the nodes as tokens, is going to give you a matrix of the good size. So we do 2 cross attentions, one per row and one per columns. Okay, and then we scale. The thing is, those 2 cross attention, cross attention, you do softmax. So every column sums to 1. So you cannot do unbalance with that because the sum, you basically have the constraints on the marginal here. So what we do is we take this attention by row, and then we scale the row. So we have another head that actually predict the scaling of the rows. Okay, and so the second one is done the same but transpose basically, and then we do the sum of the 2. So what it gives us is basically the output of our neural network is a weighted sum and scaled attention matrices, which makes a lot of sense because when you think about it, an optimal transport plan is going to predict the relations between the point on the left and on the right. So the cross attention is a good way to encode this pairwise relationship. So that's the way we do in ULOT. because of the unbalanced aspect, we need to scale the columns and the rows, which is a bit challenging. For Grail, it's simpler because for Grail, we fix the number of nodes. You remember I said we have m maximum nodes with the padding. So for Grail, we have a fixed number of nodes, so we just need to predict a permutation. So what we do is we use node embedding and we do an optimal transport, a smooth optimal transport, a sinkhorn to actually predict. So the head of the predictor here is a sinkhorn algorithm. So we use embeddings, we learn embeddings so that when you do the sinkhorn, it's going to predict the best optimal transport plan for you. Did I give you more information about the architectures?
Yeah. Thank you very much. Thank you for explaining that in a great detail. Thank you very much. Now it's clear.
Any other questions?
Okay, I have one of my own. So, Gromov-Wasserstein famously metrizes the equivalence class of isomorphic MM spaces, right? So, do you have any idea of a test to check the graph isomorphism between two candidate graphs or the space of graphs? So do you have for example, we have OT-based test of stochasticity between two distributions, right?
So fun
So do we have?
fact, I know there are tests on the traditional OT, with Wasserstein.
Mhm.
There are papers about that. I have not seen actual test using Gromov. So that could be a nice idea. The thing with Gromov is that you can probably do the theory of a test. Actually, in the paper of Valle, so not the first one, but the second that's called Fused Gromov-Wasserstein, published in the algorithm journal, we actually have a speed of convergence of the Gromov-Wasserstein and the fused Gromov-Wasserstein as a function of the number of nodes, if they are IID from distribution. So I think we could come back to test. But it's basically the same convergence speed as Wasserstein, so it's not gonna handle well high-dimensional data.
All right.
But that's an interesting question.
All right. Thank you.
I have a quick question. So regarding the optimization, does it make sense to do it in a hierarchical fashion? For instance, let's say you have two graphs. You first coarsen the graphs in some way, then find OT matching between the coarsened graphs, and then focus on the matched coarsened subparts, right? And do a
Yes.
smaller OT problem there.
Yeah. So there are papers that does that actually. So it's one way, but I mean, doing that it works well, okay? Because you coarsen, then you solve a smaller problem, and then you can fine tune. To my knowledge, you still also lose, some subtleties, and so the coarsening can basically. Basically, you might not reach a zero where even for two identical graphs, depending on how the coarsening works. You see what I'm saying? So
Yeah.
There are ways to do that. Also, and that's actually changing because we are working on the solver on input at the moment. But the idea is that when you do hierarchical, so it works. Actually, there are a lot of solvers that work like that. Okay, for instance, there is a low rank solver for Gromov that is exactly that. Basically, you search for a plan that is low rank, which corresponds to doing community clustering at the same time as you do optimal transport. So it's not a two-step process. It's like one step where you do all of that together. And so those are nice methods. They are quite fast, but the plan is quite dense at the end. And so you lose, the one-to-one mapping that is quite interpretable, and that I kind of think is important, especially on graphs such as molecules or these kind of things.
Right. Excellent. Yeah. Thank you. Any other questions? Yeah, I mean, if not, then we can thanks Professor Flamary for the very interesting talk and answering all these questions. Thank you.
So I have just one more question. So is can be used for hypergraphs?
Yeah. So there are extensions that work on hypergraphs. Yes. Basically, look, I'm gonna show you here. Actually, it's quite simple. It's a bit subtle to implement well, but it's quite simple. It's here, here I compute the distance between pairwise matrices. Okay, but on a hypergraph, basically, you would have a tensor here, and you can do the distance between the tensors at ik. Okay, so if you have an hypergraph, you can still extend Gromov.
Okay.
And I think we might even have something that works in pot, but I'm not sure. You have to check the documentation because we have a lot of solvers, so I'm not sure.
Okay, thanks.
Yeah, thanks a lot. So maybe let's have a virtual clap for Professor Flamary.
Thank you.
Yeah.
Thank you, Professor.
All right.
Thank
Thank
you,
you,
Professor.
everybody. And with that, I'll end this session then.
Okay.
Yeah.
Goodbye.
Yeah. See you on the other side. See you soon, I guess.
Yeah.